Hello. Today we're going to look at what's something called logarithmic differentiation. It allows us to take the derivative of some complicated functions by kind of doing a little trick using the rules of logarithms to help us simplify. Remember the rules of logarithms. I will remind you the basic rules of logarithms. And again, I will only write this in terms of natural log. Natural log of a times b is the natural log of a plus the natural log of b. The natural log of a divided by b just assumes that a and b are both positive, by the way, is equal to the natural log of a minus the natural log of b, and the natural log of a to the r is r times the natural log of a. These are simple basic rules of logarithms. So if I have a complicated function that basically have parts that are combined by powers, multiplication, or division, we can use the rules of logarithms to help us. For example, suppose I have y equals tangent squared of x times 2x plus 1 quantity cubed over the cube root of x, and I want the derivative of this. This is a really nasty thing to take the derivative of in this form. What we can do is we can take the natural log of both sides. Take the natural log of the entire side. With that, then, I can break this apart using my rules of logarithms. This is going to become the natural log of tangent squared of x plus the natural log of 2x plus 3 quantity cubed. That's using my first rule in the numerator. Using the second rule in the denominator. For the denominator, natural log minus natural log of the cube root of x, which, by the way, is x to the 1/3. And then using my bottom rule, this becomes 2 natural log of tangent of x plus 3 natural log of 2x plus 3 minus 1/3 natural log of x. Okay? And now, with that, let me bring this down. I will now take the derivative of this using implicit differentiation. So, 1 over y dy dx is equal to 2 over tangent of x times secant squared of x, the derivative of natural log of tangent of x, plus 3 over 2x plus 3 times 2. I'm using a chain rule on all of these. Well, except for the last one, minus 1 over 3x, 1/3 times 1 over x. Which means my derivative, dy dx, is 2 secant squared of x over tangent of x, I'm just going to leave that like that, plus 6 over 2x plus 3 minus 1 over 3x times my function y, and I don't want to leave that as plain old y. I will write back what we started with, so my derivative, and I'll write this now as y prime, is 2 secant squared of x over tangent of x plus 6 over 2x plus 3 minus 1 over 3x times my original function tangent squared of x times 2x plus 3 quantity cubed over the cube root of x. If I wanted to, I could distribute that back through, but I'm going to leave it like that, partially because I don't feel like it, and partially because I'm out of room. Okay? One more example. This particular, before I erase this completely, we could have taken the derivative of this function using the product rule, power rule, chain rule, quotient rules, all involved in all of this, and we would have ultimately ended up with the same result. It would have taken a whole lot longer, and more than likely we would have made a mistake, at least some of you. But we could have gotten that result without using logarithmic differentiation. The last example that I'm going to give you requires logarithmic differentiation. Y equals x to the arctan of x. Now, the reason why it requires logarithmic differentiation is because this is not a form that we have dealt with. This is not a power function where I have a variable in the base and a number as the exponent. It is not an exponential function where I have a number in the base and the variable in the exponent. In this case, I have variables both places. So we have to do this a different way. The only way you can take this derivative is using logarithmic differentiation. Natural log of y is equal to the natural log of x to the arctan of x. Using the rules of logarithms, this becomes arctan of x times the natural log of x. This comes out front. Now we can take the derivative, 1 over y dy dx is equal to, this is a product first, arctan of x, derivative of the second would be 1 over x, plus the second. The derivative of arctan is 1 over 1 plus x squared, which means that my derivative y prime is equal to what I have, arctan of x over x plus the natural log of x over 1 plus x squared times my original function y, and I will just go ahead and write that, x to the arctan of x. By the way, what is the derivative at 1? Let's see if you remember some stuff. Y prime at 1, if in case I wanted that, would have been the arctan of 1, which is pi over 4, plus the natural log of 1 is 0, times 1 to any power is 1, and so the derivative at 1 would just be pi over 4. Which means in case I wanted the equation of the tangent line, at x equal 1, my functional value is 1, that's what this is right here, and so y at 1 is 1, which means my equation would be y minus 1 is equal to pi over 4 times the quantity x minus 1. Rather simple.